Hello everyone, I'm Jiaqi Gao, a fourth-year PhD student at Harvard University. Today I'm going to present Lyra, a cross-platform language and compiler for data plane programming on heterogeneous ASICs. This work is done during my internship at Alibaba. Recently, programmable network devices have gained significant traction in the networking community because of their high performance and high flexibility. People have shown the tremendous benefits brought by the flexibility of programmable network devices, for example, consensus protocols, load balancing, network monitoring, storage, and congestion controls. All of the mainstream vendors are releasing their own programmable ASICs. However, despite the bloom of the programmable network devices and languages, we found that the foundation of network programming on data plane is still at an early stage. Just like the era when the programmers coding the software on CPU using the assembly language, network programmers are still using chip-specific languages and manually take care of the numerous details with hardware features, capacities, and network environments. In general, there are three problems when programming the data plane. The first problem is portability. Current data plane programs are tightly coupled with specific ASIC models from specific vendors. It cannot migrate across different programming languages, such as Trojan 4 supports NPL, while Silicon 1 supports P4. It also cannot migrate across different chip architectures with same language support, such as Silicon 1 and Tofino, and sometimes cannot migrate between different models by the same vendor, such as Tofino and Tofino 2. As a result, programmers are required to be proficient in all the data plane languages and all variable architectures and resource constraints of different ASICs. The second problem is the extensibility, which means to distribute a program across multiple switches. Low-level languages focus on programming individual ASICs, while there are data plane programs that require to execute on multiple ASICs in a distributed way. For example, a network service chain may assign different roles to different switches, such as firewall, gateway, and load balancer on each of the switches. On the other hand, applications such as firewall can also collectively use table resources in multiple switches for accommodating large-scale workloads. Nowadays, programmers have to individually program each switch data plane. Last but not the least, the practical deployment of the programmable data plane must have multiple programs enabled. For example, the programmer may wish to deploy both the ARP function and firewall function in the same switch. Currently, the programmer has to manually merge the programs together. We believe the fundamental reason for the above three problems is the lack of a high-level data plane programming language. Like we've said before, the low-level chip-specific language is the same as the assembly language that is specific to the architecture. Just like Dr. Brand said, the C language lets you get close to the machine without getting tied up in the machine. So now it's time to propose the high-level data plane language. So here we present Lyra, a high-level data plane programming language and compiler. Lyra offers a one-big pipeline abstraction. It is the interface we provide to the programmer that hides the pre-mentioned three challenges. The programmers only need to write down their intent through the Lyra language. The Lyra compiler can solve the three challenges and compile the program into the chip-specific program for each switch. Let's first see why we need a new abstraction. Traditionally, there are two models of the network. The first model is a per-switch model, where the programmers program each switch individually. And as we introduced before, this model is too fine-grained and brings many challenges. On the other side, we have the one big switch model, which treats the whole network as a giant switch, and the switch is only in charge of delivering the packets between the servers. This, on the other side, is too coarse-grained that we cannot control where to allocate the programs, such as deploying an ARP table to all of the TORs. So we choose a one big pipeline model that provides a good balance that gives enough flexibility to the programmers, but not let them tied up to the detail of the topology. The one big pipeline model achieves the portability because it hides the switch chip information. In this model, programmers no longer need to worry about how to split the code between switches. Here, the programmer can simply assign the firewall to be deployed in these two switches and deploy the pipeline of code in the red scope. At last, the programmers can simply composite multiple programs together by overlapping the deploy scope of the pipeline. In this case, the programmer can deploy the ARP program in each Tor switch. Now let's see how the Lyra compiler compiles the program into the chip-specific low-level languages. The Lyra compiler has two components, the front-end and the back-end, and here is the input Lyra program. The front-end translates the input Lyra program into the intermediate representation. The Lyra backend compiles the intermediate representation into a data plane program on each switch. Let's take a closer look at the backend of the compiler. Remember previously, there are three challenges: portability, composition, and extensibility. The backend introduces three components to solve each challenge. Lyra first builds one language synthesizer for each language, such as P4 or NPL, to synthesize structured chip-specific programs. Because the low-level languages have different programming paradigms, we need to develop the language synthesizer in parallel. For example, to synthesize a P4 program, we introduce a special data structure called the predicate block. Next, Lyra uses a chip-specific constraint encoder to check whether the program can fit into the switch. To achieve this, we implement one encoding algorithm for each type of resource to estimate its usage, such as the packet header vector, SRAM, TCAM, etc. Please refer to our paper for the complete list. At last, the distributor uses the topology and the pipeline deploy information to deploy the program across multiple switches. The backend uses several constraints to make sure the program is correctly deployed in the network. For example, the upstream switches have to pack downstream required information in the packet header so that downstream switches can process the packet correctly. The above three components encode the input Lyra program into an SMT formula, and the SMT solver returns a valid allocation plan. At last, this allocation plan is translated into the data plane program running on each switch. To evaluate the performance of the Lyra compiler, we wrote Lyra programs for applications such as netcache, netchain, and even switch.p4. There are two takeaways. The first is Lyra program requires way less line of code than P4 program. We can see from this table, Lyra saves 30% to 80% line of code compared with the P4.14 implementation. This is because Lyra uses a more compact language framework and a one big pipeline model. The second takeaway is that Lyra can reduce resource usage. We can see that in the netcache example, Lyra uses only 12 tables, while the original program uses 96 tables. We observe similar gains for other programs such as netchain and speedlight. This is mostly because the manually written version kept many independent tables for modularity, but Lyra merges these independent tables together into a single table. Here is a code for netcache. We can see that there are two tables with no matching field. And because they are executed under different branches, they can never be executed at the same time. The Lyra can merge these two tables into one table and two rules that matches the nc_hdr.op field, which is shown on the right. We also evaluated the scalability of the compiler. Please check our paper for the result. Here summarizes the can and cannots of Lyra. Lyra can generate the data plane program for the entire network. It supports P4.14, 16, and NPL data plane languages. And it supports both stateful and stateless operations. It can also reduce the resource usage compared with human-written programs. But Lyra is not responsible for generating the control plane programs or configurations. At last, currently Lyra generates data plane programs from the beginning and does not synthesize incremental changes. In conclusion, Lyra is the first high-level data plane language and compiler that achieves portability, extensibility, and composition. Lyra offers a one big pipeline programming model and can generate runnable chip-specific code across multiple switches. The programs generated by Lyra use fewer hardware resources than human-written programs. Thanks for listening, and I'm happy to take questions.